We're going to finish this chapter today, our first dynamics chapter today. We got a number of demonstrations. And the first one relates to this problem that we did yesterday. This is called a static equilibrium problem because it's a static equilibrium problem. There's no motion. The mass here is in equilibrium, not moving. And the problem here, given this mass and this angle and the fact that this is horizontal, find the tensions. And we found the tensions. T1, here's T1, and here's T2. So can we, a natural question is, can we verify this theory? And the answer is yes, and it's convenient here to look at it from a different perspective in here. In this perspective, we're given this angle, this is horizontal, this mass, we found the tensions. What we're going to do, what is done in this apparatus here is these tensions have been dialed up. They've been created by these hanging weights here. Because what's the tension in this cord right here?
Same as that weight.
It's the same as the weight, right? You've got this weight here. There's a gravitational force called the weight that's down. There's a tension force up. It's not moving. Those two forces have to balance each other. So the tension equals the weight, and it gets transmitted right along here. This is an ideal pulley, yeah. And so it gets, and similarly over here. Now, I've done some, anytime you do experiment, you want to stop and think a little bit and try to make, life is going to be hard enough, so you want to think and to try to make it easier. There's trouble always with experiments. So what I've done here is, first, this is T1, I think, right?
Yeah.
Okay, what mass do we put on here to get the predicted tension? Well, the relationship is very simple. As you just told me, that the tension is the weight. So the mass we want to put on here, when multiplied by g, that'll be the predicted tension. So this is the mass we should put here, this, and this is the mass we should put here, and this would be our 3 kilograms. These are way too heavy for an apparatus like this. So I'm going to divide all the masses by 10. I'm going to scale them down by 10. And the reason we can do that is the predicted tensions in here are proportional to m. M is scales everywhere here, and you can see that in the theory. It's reasonable, and you can see it in the theory. Look at T1 is proportional to m, T2 is proportional to m. So if I divide all of these masses, m, m1, and m3, by 10, we're still going to have a solution. We're going to have, the theory is going to predict that we have this, and that that should be 40 degrees, and that should be horizontal. So that's what I've arranged here to the nearest gram. I've include, of course, the weight hanger. It's a 50-gram weight hanger in each of these cases. So you have to include that. It's the total hanging weight that's important, obviously. And you can see here that this is almost horizontal. It's rising a little bit as you go this way. There's a little bit of error there, but it's close to being horizontal, right? And what about this angle here? It's a little hard to measure because I have to extrapolate this up here. But when I do that, as best I can, yeah, looks like it's very close to 40 degrees. This angle is close to 40 degrees. So that verifies the theory. But there's always with experiments, there are interesting, sometimes you call them problems, sometimes you call them interesting aspects. I don't know if there's any clear distinction there. But I want to show something to you. Is this the only equilibrium we can arrange here? What if let me pull on this, okay? And let me slowly let it relax to equilibrium. I don't like these things oscillating. Let me see if I can stop that. So I'm going to slowly let this come to equilibrium. Now what do you see? This is definitely not horizontal now, right? I wonder if this is 40. Pardon me?
Probably less than 40.
Right intuition. I don't know if we're going to be able to detect it, but you're right. That's what we would expect here. Oh yeah, it's like 35.
Is that just because of the friction?
Yes, it's the friction in the pulleys. How do we get rid of friction in the pulleys? Well, you can do what everybody in the world does. Get WD-40. That can help, right? But there's another way. You notice I had to carefully arrange this, right? And I could go the other way too. You vibrate the apparatus. That'll break the static friction. Help it find its true, genuine equilibrium. This is an equilibrium that's where the friction is playing a role. Okay? So I can vibrate the supports. I can like this. It seems to be better to bang on the table. Now what do you see? Wow. Pretty horizontal, right? Do I need to measure this? No, it's going to be close to 40. Okay, any questions about that? Okay, next problem. We're doing applications of Newton's laws. Our first set of applications of Newton's laws. This is a standard problem. You've all solved this problem. You may not remember it. This is we got two masses now, not just one. But the idea is the same. We're going to apply Newton's second law to each of these masses. And the problem here is to find the tension in the string. And this is an ideal pulley here. Massless, frictionless, uniform gravitational field. No friction on this surface here. This could be an air track. We want to find the tension and the acceleration, the magnitude of the acceleration. Well, wait a minute. Do these things have the same acceleration? Well, this one accelerates that way, and that one accelerates that way. So the direction's not the same. But what about the magnitude of the acceleration? Yep. Why is it the same? You have the right intuition. I don't know if you can explain it. How do you explain it?
Because they're connected. It has to be, right?
It has to be?
Because they're connected. So if one's moving one way, the other one has to move the other way. It's the same thing with the weight and the tension, right?
No, I wouldn't go there.
Unless that chords are bunched.
Well, we have motion now. And the tension, what's the tension in the string? M2G? Nope. If the tension were M2G, would this accelerate? No, there's a weight of M2G down, a tension this way, it wouldn't accelerate. The tension has to be less than M2G. That's going to be a check on our solution. So don't think about that. But you all have the right idea here. We're going to assume this string is inextensible. You can't stretch it, right? It has a fixed length. So any change, if this changes over an amount of time, this is going to move a little bit, this a small time, this is going to move a little, this is going to move a little bit. They're going to move the same distance, right? In the same amount of time. So they're going to have the same instantaneous velocity, and they're going to have the same acceleration, magnitude of the acceleration, and magnitude of the instantaneous velocity. So we're going to find that common acceleration. So this is how do we solve these problems? Here's the picture. What's next? Once we understand, we have to understand that.
Force diagram?
Yes, two force diagrams now, right? Here they are. So here's this mass, M1. It's a force of gravity, the weight. There's a normal force by the surface, directly upward. We're neglecting, no friction, we're neglecting friction. And then there's this tension force. Here's mass 2, same tension magnitude, right? Same tension. Tension, most people, when they, as I told you, most people when they say tension, they're thinking magnitude. So the tension just gets transmitted here, because it's an ideal, massless string. And here's the situation, the force diagram for this mass. Gravitational force or weight down and tension up. Then, next step, write down Newton's laws. So here we've got two dimensions here. What's got to be the force in the vertical direction? The normal force has to be m1g because there's no acceleration. If these weren't equal, this thing would be rising, it would be accelerating upward or digging down somehow into the table or the surface there. So n has to be m1g in this case. T will be m1 times the acceleration. That's Newton's second law in the x direction. Over here we just have the y direction. And now, oh, I didn't realize this. We have to be a little careful here. We're choosing this as our positive direction, right? So when we go over here and go down or here, this is going to be our positive direction there. So this is a positive force, that's a negative force. Okay, we naturally do that because of what we've chosen up here. What we've chosen up here to this be the positive direction, that forces down to be the positive direction. Forces us to do that. Okay, we have 3 equations and how many unknowns? Let's see, we don't know A, we don't know T, we don't know N. So 3 equations, 3 unknowns, looks good. They're linear equations, that's even better. And the first equation tells us what N is, which we really don't care. It doesn't really help us solve. We want to find T, the tension T, and the acceleration A. So discarding this because we don't need it, we have 2 equations and 2 unknowns. 2 linear equations and 2 unknowns. So it's easy to solve. And you can make it, the easiest way to solve is look at on these 2 things. What if you can take this and substitute it and use the substitution method, what they call it. But I want you to imagine taking this equation, putting it underneath here, and then add the left sides and add the right sides. What's going to happen? Can you see that? The t's cancel. And so that's the quickest way to do it. And here's what we find. When we do that, we have a single equation and a single unknown A, easy to solve, and we get this acceleration. Once we got the acceleration, we're essentially done. We can get the tension very easily. The easiest thing to do is, here's this equation is the simpler of the 2. So once we have the acceleration, we just put the expression in there and we can find the tension. So we've now solved for the acceleration and the tension. Now this is these are formulas. They hold for any values of the masses, and for G, so we can check it in special cases. Before we go on, I want to point something out though. It's not in the notes, and sometimes it's dangerous at this level. But look at this right here. Bring this up here to the numerator. What do you see? You see F is equal to ma, right? Here's the driving force for the system. Here's the total mass of the system. Here's the acceleration. Wow, what's that? Oh, phone. So I don't want you to do this, okay? Because I think it's dangerous. That's why I left it out of the notes, but for some reason I'm telling you now, I have no idea why. You can look at this and actually write down the answer. You can write down equation 1, you can write down what the acceleration is. You can imagine rotating, get rid of the gravitational field of the Earth, rotate this up so it's a one-dimensional problem. But keep the force on this. The force is m2g. So I can come up with an equivalent system. I have no idea why I'm telling you this. I really should not be telling. This is, you learn that. So this is the lowest level, right, of mechanics, and so this could be really dangerous. But I encourage you not to use this to solve problems, okay? But I just can't. For some reason, I can't stop myself. So here's the force. I just got to go with it. So we can write down. What do we write down here? I can go ahead and imagine these just to be one mass, right? That doesn't change anything. So F is equal to m times A, right? So trick. Don't do it. Don't use it. You're just asking for trouble. That's my experience with students, okay? But I guess the reason I'm saying it is, we can think of this as a check on our solution. Even though this is there could be dangerous to do problems this way, these kind of shortcuts. This has got to be right. We just re-derived it, didn't we, from a simpler point of view, if you think a little bit about it. Okay, now, first thing, the tension is not M2G. Remember, we talked about that? You might think, oh, this tension has to balance that. It can't. It has to be less because this is accelerating downward. So let's see if our expression yields of tension that is less than M2G. Well, here's M2G. If I look at what's multiplying M2G, that's a number that's got to be less than 1. So we do indeed have T less than M2G, which has to be true. So that's a check on our solution. So the other thing that people do here, and everybody does this no matter, and especially in research, you've got to check special cases where you know what the answer is. So here's a simple one, and usually these are very simple. No gravity. So what's going to happen if I release this thing from rest? There's no gravity. It's just going to sit there, right? The acceleration should be 0. Or if I give it some initial velocity and there's no gravity, both will move with the same constant speed, right? So what does our theory say when G is equal to 0? A is equal to 0, that's right. Oh, and what's the tension? The tension's 0. Right, there should be no tension here. You know, let's take the simplest case. I release this from rest and where there's no gravitational field. The tension's there due to gravity. You remove gravity, there's no tension. And sure enough, we get 0. Now, this may sound silly to you, like a waste of time, but again, when you're doing research, doing something no one's done before, and you got some expression that you derived, you're always worried that it could be wrong, right? So you want to check, especially in that case, and it's a good idea to start doing it now, this level. Just check. It's easy to do. Here's something you might not think about, but what about the case where, let's say, M1 is much greater than M2? What's going to happen if this is really heavy? And again, there's no friction here compared to this. What kind of acceleration are we going to have? It's going to be small, right? In fact, in the limit, as m1 goes to infinity, the acceleration should be 0. So let's see what we get for large m. And by large m, we mean relative. The proper statement is large compared to m2. So the acceleration, when m1 is much greater than m2, I can neglect this. m1 is much greater than m2, I can neglect this. And then I get that the acceleration is m2 over m1 times g. That's small by assumption. By assumption, m2 is much less than m1. So our answer is reasonable in that case. We're getting a small acceleration, small compared to g. Because this is a small number here, m2 divided by m1. What about the tension? What does our theory tell us the tension is when m1 is very large? Well, I killed the m2 because m1 is very large, and then what can I do? Cancel the m1. So I get m2g. Is that right? Yeah, it's essentially a static system, and the tension's got to be m2g. So that deserves, like this one, a check mark. Finally, you can do you can flip this limiting mass ratio case. You can imagine m1 to be very small. So if m1 is very small, what acceleration is this going to have? There's going to be essentially no tension in here. If m1's really small, it's just g. We should get g. So let's see if that's right. So when m1 is much less than m2, we get this, we cancel, yep, m1g, it works. And oh, by the way, what's the acceleration when m1 is very small? We neglect this, we get g. It should be g, so it works. Now we're beating these problems to death right now because these are our first set of problems. We won't do this we're not going to make it a habit of this, okay? Okay, any questions about that one? So here's an old problem. It could be 100 years or more old. And it's interesting. You've got frictionless surface, two masses, they're up against each other, and you exert a force here. Okay, and we're going to find the contact force here. Now, what do I mean by contact force? M1 is going to exert a force on M2, and M2 will exert an equal and opposite force on M3 by Newton's third law. So there's really only just one force there, and we usually call it the contact force. And then we're going to flip the force, and instead of having it applied to this mass this way, we're going to apply it that way. And we're going to see how things change. Okay? So, now I need to fix this. I've introduced F2 before I've introduced F1, but this is just convenient here. This, we're going to let F2, here's the applied force, here's what we're given, right? The masses and the applied force here. We're going to call F2 the force of 1 on 2 when we apply the force this way. We're going to call F1, when we flip the force, the applied force, we're going to call F1 the force of M2 on M1. So it's natural to use that notation. So, how do you proceed here? Well, it's not, maybe it's not obvious. So when things aren't obvious, you just start kind of writing down what you know. I know that we just, remember this? This is going to act like just one mass of value M1 plus M2. So I can write down Newton's second law for that. There's just one force, there's the total mass, there's the acceleration. So we found the acceleration. The acceleration is going to be given by this, and if we plug the numbers in, it happens to be 0.914 meters per second squared. So now, once we know the acceleration, I know that this has to have the same acceleration, right? But what force does it feel? What force does it feel? It just feels the force of M1 on it, which we're calling Mf2. So it has to have the same acceleration that we just found here. So Newton's second law applied to this mass is going to be this contact force that we're after, because that's all that it feels. This weight is balanced by the normal force, so I'm not worried about that in the perpendicular direction, and there's no motion in that direction. So this tells me how to calculate the, because now that we know the acceleration, we can find the force of M1 on M2, that contact force. And here it is algebraically. It's easier. What I've done here is confusing, and I need to fix this. I just wrote down the algebraic expression, but having found A, we can just substitute it into here, right? That's what I did right here. So I'm going to fix this, make it look better. So I'm punching it in here. It's just easier. And we get about 1.1 newtons. Okay, now, yeah.
I mean, just if you're able to click, why do you use M2 or the mass of 2 versus the mass of 1? I guess kind of conceptually.
Okay, we're after this contact. We're after the contact force. So I guess in a sense, I'm just writing down what I know here. I'm just, but we are asked. The problem here is to find the contact force, and so I think I know what's bothering you. We could write down, excuse me?
Because I feel like it's M1, the mass of 1.
Yeah, we could write down Newton's second law for M1, but why would we rather write it down for M2? What are the forces on M1? There's two forces. You could do the problem that way. You could find the contact force that way. It's a good point. But look, there's this applied force on M1, and then there's the force of M2 on M1. It's just a little bit more complicated. That's a very good point. You could do it that way. All these problems, there's a variety of ways you can do them. Okay, so we've found the contact force, which we call F2. That's when you apply the force this way. Now we want to apply the force the other way. And now we would do the same, we're going to do the same thing. We're going to focus our attention on M1 because there's just one force on M1 now. That's going to be the force of M2, and we're calling that F1. So we do a similar thing, and we find a different answer. It's like roughly twice. So if you were sandwiched, here's the standard issue, the question that's brought up here. If you were sandwiched between these two masses, and I'm gonna beef these up by a factor of 10. We need to make this beefier, okay? Because I want you to imagine being sandwiched in here. Which would you rather be sandwiched? If you have to be sandwiched in there, would you rather the applied force be applied here or there?
Well, no, it's F2. I want to be pushed on F2.
So
It's less force on me as a person.
that's right. So this is the situation, right? Does that make sense? You know, the contact forces are different. At first you might think, oh, you apply a force this way, you apply a force that way, the contact force is going to be the same. But it's not. But it's actually obvious.
Larger mass.
What?
So you have a larger mass.
Yeah, in fact, that's the key. You want to go to extremes. You want to, it's called reducing it to an absurdity. They used to say that in Latin. But seriously, I know it sounds weird. It sounds better in Latin. What?
And it's because that initial force it's overcoming the stress. The larger mass has a. I don't even know how to.
Yeah, I know what you're thinking. It's easier to keep something going than to get it going.
Right.
That's because of friction. There's no friction here. It's subtle. Yeah. With no friction, you apply force. This thing is going to start from rest and it's going to accelerate. And it's going to have a constant acceleration. But what you're thinking, you're throwing in friction. A very common thing that it's easier to keep something going than to get it going. We'll talk about that later in the course, friction. So look, let's go to extremes. Let's imagine that M2 is much less than M1. These two have the same acceleration, but it's much less mass. So what does the contact force have to be in that case? It's got to be small. It's got to be small. Right? And if you put the force over here, with M2 being very small, you're going to have a big contact force because this is much bigger mass. So it has to be true. Like Damon said, you'd want to be, this is the situation, if you're going to be sandwiched here, you'd like this one with M2 being less. We see that it has to be true by going to extremes, right, where M2 is very small. And the limit as M2 goes to 0, what's the contact force? 0. Yeah, it just gets, as you reduce M2, the contact force here just gets smaller and smaller. But not this way, not that way. Yeah, it's an interesting problem, and like I said, it's been around a long time. I remember it seeing it decades ago. Okay, any questions? Okay, so now what we're going to do for the rest of the lecture. There's a few pages here. Okay, we're going to look at mechanics in a non-inertial frame of reference. We're going to normally, especially at this level, you do everything in an inertial frame of reference where Newton's laws hold. But it's sometimes very useful to look at things in an accelerated frame of reference. And you'll see that when we go through these examples. So the first one is apparent weight. We've talked a little bit about this before. So here's an elevator that's accelerating, that has some acceleration. We're going to choose up to be positive acceleration. But that A here, this acceleration A, could be 0 and it could be negative. The elevator could be, we want to be very general here and you'll see why. We want to be able to cover different situations. Okay, and you're standing on a scale, and the question is, what does the scale read? What's your weight? What is the weight reading of the scale? Well, we know that first of all, that your true weight is just going to be mg, right? And most of you intuitively know the answer here, and we've actually talked about it before. If this is accelerating upward, is the scale going to register? Is it going to be bigger or smaller? It's going to be bigger. And if you're decelerating, if you're slowing up, going up, or if you're accelerating, downward. If the proper way to say this, if A is negative, okay, then it's going to read less, right? So how do we quantify that? Well, you just have to think a little bit, okay? Do you guys see there's a prime here? I don't know if okay. What all that scale knows is there's a person standing on that scale, and what it's going to read is let me start off with the person. There's a normal force on the person here. That's the force of the scale on the person. It's pointing upward. There's a normal force. What the scale reads is that, by Newton's third law, is that equal and opposite force. It reads the normal force. That's the magnitude it's going to read. So we need to find the normal force. How do we do that? We have a picture, force diagram, write down Newton's second law. Okay, so we have a picture. Here's a force diagram. Now, you see I've drawn this one bigger because I'm thinking of it accelerating upward, but we're going to cover all cases. Our theory here is covering all cases. So Newton's second law tells me that we're choosing up as positive. N minus mg has to be the mass times the acceleration. The net force, which is n minus mg, has to be the mass times the acceleration. Well, I can solve that for n because that's the apparent weight. The apparent weight is the normal force. I solve it for n, and I get, this is convenient, but right now we're just going to, this form is convenient, as I'll explain to you in a few minutes. But we see that the apparent weight is indeed different, and when A is positive, what's the apparent weight? It's greater. When A is negative, it's less. All right? So you've all felt this in an elevator. Right, when you walk into an elevator, and when it's not moving, you feel normal. The scale would read your normal weight. When it starts, let's say it accelerates upward, it's going to be heavier, okay? And it's going to be by this amount right here. Given an A, a positive A, the weight will be greater by that amount. When it has negative acceleration, it'll be less by that mass times the acceleration. So you feel heavier when the elevator starts off. When the elevator then reaches constant velocity, what's the scale reading for constant velocity? Normal. There's no acceleration. It's going to be normal, and I'll demonstrate this for you in a minute. And then what happens when you slow down? Right. Okay. Now, one interesting thing here is, what if A equals minus G? What does that correspond to? That's a freely falling elevator. There's nothing stops us from doing that. A freely falling elevator will have an acceleration equal to, we've chosen up to be positive, so A will be minus G. What's the weight?
Your normal weight.
What's G minus G? 0. You're weightless, and you need this. So it's as if you've eliminated the Earth's gravitational field. A freely falling elevator. If somebody's in a freely falling elevator and they can't see outside the elevator, which is usually the case, you really can't tell any difference between being in that freely falling elevator on Earth or being out in deep space. Now there's a caveat there. Well, let's just leave it at that, okay? So you can't, I don't want to get into details here. So does that makes sense, right? I mean, our theory is telling us that. When you're in a freely falling elevator on the Earth or any other planet, you don't feel a gravitational field. Everything's weightless. I want to look at something accelerate due to gravity. I let this go. What does it do? It just sits there. I see it as just sitting there. So this may sound like it's not very useful and not very interesting, but it's the cornerstone of Einstein's general theory of relativity. And he started wondering about this stuff when he was 16 years old. Okay? And it took him about a decade to do what's called the special theory of relativity. That's where mass is not involved. That's just how different people observe things from different frames of reference. When you throw mass in, it becomes a lot more complicated. But what he did was, he showed that Newtonian physics is wrong. All the stuff we're doing is technically wrong. What we're doing is an extremely good approximation in typical cases. But if you have velocities near the velocity of light, or if you're near a black hole, okay, Newtonian physics breaks down. And he came up with what seems to be the right theory. There have been competitive theories, but as the data comes in, they're falling by the wayside. And his theories of so-called special and general relativity have held up. So he used this when he constructed the general theory involving gravitation. It's called the equivalence principle. So the idea here is that you're in a uniform gravitational field. You can look at it from another perspective. I'm in this uniform gravitational field, right? But if I couldn't see outside, and this entire classroom were transported to deep space, and somebody caused it to accelerate upward at 9.8 meters per second squared, we can't tell any difference. They're equivalent. Those two situations are equivalent. So it sounds, not that interesting, but he got a lot of mileage out of it. Like I said, it's the cornerstone of his general theory of relativity. Okay, so this should be up here. That's what we're saying here, what I just said. Here we're in a gravitational field. You can't tell the difference. Okay. Okay, I'll tell you what was bothering me before. Okay. If you're very careful here, this is going to be a strictly uniform gravitational field. If you take very careful measurements here, is the gravitational field going to be uniform? No, because you're closer to, the closer you get to the Earth, the gravitational field, the strength goes up a little bit, right? So the equivalence principle stated properly, and I'm just way beyond this course right now, okay? These two are equivalent locally, as long as you're in a small spatial region. The equivalence principle is true locally. If you go on a big scale, if I make this bigger and bigger, eventually, way over here, thousands of miles over here, I'm going to see, G pointing this way, right? Because of the Earth, because it points towards the center of the Earth. Okay, but so it's actually true locally. That's all Einstein needed to forge ahead with the general theory. There was a question. Yeah.
At what point does gravity stop being 9.8 meters per second? Like, how high up do you have to go?
Well, so what's the answer to that question? That's a good question. It's a standard kind of question.
Even on Earth, it's different.
So here we have, right here, there's a certain acceleration due to gravity. What is it here? Is it exactly the same? No, but it deviates by an extremely small amount. So it's something that just continuously happens. As you go up, it's continuously and slowly going down. Eventually, you'll be able to measure it. It depends upon how much money you've paid for your equipment, how good it is. But in principle, if it's exactly, let's say it's, for argument's sake, it's exactly 9.8 meters per second here, let's just say. What is it here? It's a little less. What is it down here? It's a little more. It'd be very hard to measure, but everyone agrees that it's different. So the question you ask, the answer is it's all relative to what you care about, what you're sensitive to. There's no absolute answer to your question. It depends upon what problem you're dealing with. And if you want to measure it, what kind of equipment you have. So there's no, I can't answer that question. Sorry. but it's actually a common type of question. I get that a lot, where people want to know, they want to simplify things. I say, well, okay, so how high do I have to for G to change? There's no universal answer to that. It depends upon what you're interested in. That's where you have to put input in, what you care about, what kind of problem you're dealing with. It's a good question. It's a good question. Any other questions? Okay. So, on my computer somewhere.
Throw it in there, I'm not sure, right?
Oh, wait. Hold it. Where's the, oh, God. You guys got to tell me. We got a demo here we have to do. Sorry. Okay, so Okay, so this reads, this is not a very accurate scale, right? And I've been dropping it, you'll see, intentionally. So this reads between 9 and 10, okay? It's 1 kilogram. It probably doesn't read, yeah, it's down to 9.5. Okay, it'll get worse, but that's not important, okay? So if I move it with constant velocity, now I'm going to start here, right? But if I'm going to move it with a constant upward velocity, there's going to be an acceleration. So I'll try to smooth that out so you don't see it. But when I move it at constant velocity, what do you see? Okay, yeah, I need to be more sensitive here. So you can see what happened, right? When I accelerate, it's going up, as it must. The tension here, force has to go up. But if I move it, shaking. Move it with constant velocity, it's approximately the same, right? If I give it a fair amount of acceleration, now, what's the problem? You see the problem with this demo? I'm going to give it some bigger acceleration now. But as soon as I do that, I'm going to have to give it a negative acceleration because I can't just keep accelerating upward. I got to bring it to rest eventually, right? So what you expect to see is it weighs heavier, and then you're going to see it go lighter. And it happens kind of quickly. So I'll do it on 3. Let's go 1, 2, 3. You see that? So it should at first read greater and then read less than the 9 point whatever 5. Okay? Yeah. So, yeah, this is not, just, this can be improved. You can always improve demos, right? You got to decide, do I want to spend weeks improving a demo? That's the way it works. I know demos seem simple, and I have to fight with my colleagues on this all the time. But when you're developing a new demo, and I've done this many times, I got many publications on this, it's research. Research is research. And you hit all the problems that people hit when they do forefront research. This is called educational research, if you wanted to improve this. But there are ways of damping that motion out. Okay? There are ways of doing this. Now, can we get a constant acceleration here? A constant force that's different from the 9.5 or 9.8? Well, yeah, we can go to circular motion here. So let me do that. I'm going to have this thing go around like that. All right? But I got to do it pretty quickly, okay? So you tell me what you see. Okay. Was it higher? Okay. Yeah, it should be higher. But wait a minute. Why is it... The centripetal acceleration is this way. It's perpendicular to here. How can we get this acceleration? So when I go like this, it reads. When I accelerate upward, it reads greater because because of what we were just talking about, right? But here, the acceleration is the centripetal acceleration. It's perpendicular. Why do I get a bigger reading? This is kind of a trick question. I mean, it's a real question. Here, let me show you again. I have to really do. Is this thing vertical?
No.
No, it's at an angle here. So there's a component of the centripetal acceleration here going this way, just like when I'm doing this, and that's why it reads greater. If I made this go like this, well, I guess I can do this. I've never done this before. Well, I'm exerting, and now I know why I've never done it before. I have to exert a force here. No, it's right in the way, isn't it? I have to exert a force here. Yeah, so let me do it this way. It's not working well. Now I got friction. This thing's up against there. But you should see it as not as giving the same value. So it's giving that higher reading because it's tilting outward like that. Okay. So, free fall. The elevator's freely falling. Everything should be weightless. So let's do that. Let's I've always had trouble with this, and I finally realized, you can't use foam rubber. It just bounces off when you drop things from a height. You want to use packing material. This works great. So what we're going to do is let this thing go into free fall. So what should the weight be? Should be 0, right? In a freely falling frame, everything's weightless. So I'm going to do this on 3. 1. Now you got to watch quickly. 1, 2, 3. So it started to tumble, but did you see this? The scale reading should have gone way down. Did it? Okay. All right. So I know a person who published a paper in the, any questions? In the 1970s, or I don't know, way back then. And the paper, in a scholarly journal, the American Journal of Physics, and the paper's about this long. I'm not kidding you. It's the shortest, it's probably the shortest paper in the ever. I never thought about that. Yeah, it probably has that distinction. Maybe I can contact the Guinness Book of World Records. Right, people. I'm not going to do it, but I got to write it down because I want to think about this. So the paper's that long. What's the subject of the paper? He pointed out that you can explain the monkey hunter demonstration in a freely falling frame. So here's the idea. The monkey, and I need to add this. The monkey has just released here, okay? Has just released. The problem, remember, is where do you aim? The projectile's going to be fired right when the monkey releases. Where do you aim the rifle? That's the problem, right? And the answer is directly at the monkey. But why? Well, I gave you one way of looking at it. It was not real clear, I have to admit, okay? You might like this better. So, just after the monkey releases, we're going to go to a frame of reference that's freely falling. We're going to be in the freely falling frame of the monkey, right after the monkey releases. So the monkey is at rest, because it's just after it releases. The rifle is at rest, right? So now, if you're in a frame of reference that has no gravitational field, which is the case here because you're in the freely falling frame, where do you aim to hit something? Well, the projectile's going, in your frame of reference, the projectile just goes with constant velocity. There's no g, there's no acceleration. So you obviously aim right at the monkey. So it's, yeah, that's not a joke. It's real. Yeah, Guinness Book of World Records. I have to contact him. Let him, he might. Okay. I actually inadvertently skipped something. But, well, we talked about it. But when you're in an accelerated frame, there is effective acceleration due to gravity. So when this is accelerating upward with g, what you feel in here is g. And in general, the effective acceleration due to gravity is what the actual one is, plus the acceleration of your frame of reference. Okay, finally, this is something I've been thinking about for a long time, and I actually did an experiment on it. I never published it, and I should have. Now it's kind of late because a lot of research is done on this. What if you have a candle flame in a freely falling container? So a candle burns in gravity because the hot air rises, convection gets going, and the convection brings in fresh oxygen so the flame can burn. If you switch off gravity, what's going to happen? No convection. The flame should go out. And for a lot of time, people just assumed that it had to go out. And somebody finally did some experiments. I was one of them, but I didn't publish it. Okay? There was problems, there's always problems. So we have Gene to thank for the apparatus here. He found this. Where did you find it?
I think it like Goodwill.
What?
It was the Goodwill.
Yeah, it was something like that. And I was thinking, oh God, how are we going to make this Gene? And he comes back after leaving campus in the afternoon with this here. So here's our flame. We're going to put this over here. I'm going to light this. Now, you might be worried, well, it's eventually going to go out, right, because it's sealed. It takes a long time. Take my word for it. It takes like a minute or more. It takes a long time. So we have plenty of time to do the experiment. All right? So let's do it. And we want to drop it from as high. We want to give it all the opportunity in the world to go out, okay? So I'm going to, well, oops. There's air in here, so let me leave it. It's strange what people do, isn't it? Okay. So now, like I said, trust me, we got plenty of time. So you want to, oh, can somebody turn off the lights? That's really helpful. Both lights. Okay, everybody ready? 1, 2, 3. Now, it went out on impact. It's going to be out. But before impact, what did you see? Yeah, and it should have gone down in intensity, and it should have become more spherical. Did you notice that? Instead of a flame being like this, it should have gone down like that. Did it do that? Did you notice that? I should have told you. But it did not go out. Yeah, it doesn't go out. And that's a big surprise. And I don't know if this is completely understood. NASA has did experiments on this in the space shuttle. And they're concerned because of fires in space. You might think that fires in, you don't have to be real concerned about a fire in 0G because it's going to go out because there's no convection, right? Well, it's not true. It does get substantially reduced, but it keeps burning for a typically long time. Eventually it'll go out. So if anybody wants to know, I've made some progress on this. We made a lot of progress last year with in this class. Some people got interested and we looked up stuff on the internet. So there are different ways that this can be explained. They all seem pretty suspicious, and there are counter arguments. Yes?
Is the material then? The material providing the oxygen for the flame to continue?
Oh, I never thought of that one. The wax. Yeah, I don't think there's much oxygen in there in the material. Or the wick. No, I just don't think there's much oxygen.
Well, as
in
the
there.
burning effect happens, I mean, as it burns, does it create its own oxygen from whatever the components are?
Oh, yeah, I strongly doubt it. Along those lines, though, one theory is once you eat up the oxygen here, other oxygen is going to diffuse to take its place, because gases will like to become uniform. But the diffusion process is very slow, so I'm suspicious of that explanation. But that's the one that seems to be accepted out there.
Doesn't the heat create a current though? So
Look, I think but there's no gravity, right? So yeah, it is heating it up, but you need gravity for the hot air to rise to create. But there's no gravity now.
well, it'd be more of a random current if there's no gravity.
Yeah, that's the good idea. It could be that there's some kind we call it spontaneous symmetry breaking. It could be that there instabilities, which are very common in fluid dynamics, develop such that some of the air is flowing out and some is flowing in, like that. That's a possibility. There are other ones too. I'm going to point one out here. In the experiment we did, we got the convection set up, right? And then I switched off the gravity. Well, the convection's not going to die down immediately, is it? So that's why when I did the experiment, I dropped it off the 6th floor of the UCLA physics building. Okay, and drove it with very heavy, well, I can't get into it. But that's not true, because on the space shuttle, they've ignited something in 0G, and it's still, it takes a long time to go out. Yeah, it's really interesting.
That's really scary. Especially if you're up in